Thank you.
Okay, let me just. So I'm sorry. Thank you so much for inviting me. I think I'm sorry, Katya. I'm having this issue again of I can't seem to. Oh, got it. Sorry, it was just frozen. Thank you. Sorry. So thank you for inviting me. It's just been such a nice series, so I'm happy to be speaking in it. And this is my first time giving a Zoom talk, so you'll bear with me if I'm a little bit, if the pace goes off or something. So thanks. So anyway, I'm going to talk about using reduced order models to do inversion in the spectral domain. In particular, about using techniques where we generate internal data from boundary data. And this is joint work with Liliana Borchea, Vladimir Druskin, Alex Mamonov, and Mike Zaslavsky. So, thanks. Sorry. Okay. So one main goal is to use reduced order models to solve inverse problems. And basically, as everybody here in this seminar knows, there's an inherent ill-posedness in most classical inverse problems. And so, well, because of this inherent ill-posedness, it's very difficult, also as everybody here knows, to do direct inversion methods if we were to just use a standard discretization of the PDE and then try to do some kind of optimization to reconstruct the coefficient. It just doesn't work because of this ill-posedness, because these small errors in the forward models lead to large errors in the inverse model. So one way to think about all this is, well, suppose instead of having some kind of standard discretization of the forward problem, what if we were to have a spectrally converging reduced order forward model? So that is one with very high order convergence. So as opposed to just a standard finite difference or finite element, but a high order converging forward model. And so the approach that we're taking here with this work and a lot of the other work before this in this area has been to find reduced order forward models which match the data exactly. So one can take the data, find a forward model that's sort of, and it's in a sense the exact right size to match the data exactly. And then the idea would be, well, then the problem then transfers to, instead of extracting the unknown coefficient directly from the data, can we extract it from the reduced order model? So I'll start by considering a one-dimensional example because it's much easier to sort of describe what's going on here. So we consider a forward problem like a Schrodinger problem in the spectral domain, meaning we have sort of a lambda as a parameter. It doesn't mean we're doing eigenvalue problems, but we have lambda as a parameter in the problem. And imagine this is just a one-dimensional medium with the source on the side represented by a Neumann condition on one side. And say for now, we just have Dirichlet data on the other side, or it could be Neumann zero, but assume we have zero data on the other side. Then we could define what we call transfer function, which is just the resulting solution at zero. So we have a source at zero, and then there's a solution at zero. And we could look at the resulting solution at zero as a function of lambda. So this is the transfer function. And for the purposes of this talk, let's consider the following inverse problem. And that is, given f of lambda and f prime of lambda, prime being in the lambda domain, at a set of points B1 through B sub m, can we use this data to reconstruct Q? So again, consider the inverse problem of being given f and f prime of lambda for m spectral points and use that to determine Q. Well, this means that we'd be given 2m spectral data values to reconstruct Q on a domain. We know this is a very highly ill-posed problem, and that, of course, doesn't go away by anything we're going to do here. But I do want to point out that we can do a modified version of what I'm going to talk about today for other forms of spectral data. In particular, we don't necessarily need to have F primes. We can do things with just F, but everything becomes nicer in the case where we have F prime in terms of how, explaining the situation. So what we'll do now is show how to construct a reduced order model that matches this data exactly. And this was well known, by the way, before this work. So consider the variational form for the differential equation. So I just take, I just take the space test and trial space to be H1 with just 0 on the Dirichlet side or whatever that could be modified for different boundary conditions, and find a solution, look for a solution U in V such that that variational equality here holds for all test functions in V. So that's just the variational form. Okay, yeah. So let's pretend we were to have exact solutions to the above problem for the M spectral points. So in the world where we had these exact solutions, we could construct a subspace, a Galerkin subspace U, generated by these solutions. So we would have U to be the span of these exact solutions. If we knew them, we could do this thing. And so we could do a Galerkin projection of the solution, which is equivalent to saying, well, find the U sub G, I'll call it, for Galerkin, in this finite dimensional subspace, such that the variational equality holds for all for all test functions in the subspace. So this is a standard Galerkin formulation, and of course it's a projection of the true solution onto the span of these exact solutions, exact for particular spectral values. So for other lambdas within the spectral interval, this would be a very highly accurate solution if we had such a thing. So when you do Galerkin, you search for the unknown coefficients. So you just write the solution as a linear combination, and then by setting the test. I mean, I know this is things that everybody knows, but just to get the notation down too, by setting the test functions equal to the basis functions, we get the mass and stiffness matrices. So we'll call them M and S, and of course they're given by these formulas, which just comes from the variational problem. So for a forward solution, so if we wanted to solve for the forward solution, if we knew the true solutions in the space U, we would get the data given by F, which is just U at 0 at the spectral points. And we would solve S plus lambda M for C, where C is the set of coefficients that we use to build the solution. Okay, so given data F of Bj, B sub j, and F prime of B sub j for these spectral points, what can we do? Well, suppose we go back to the variational equality and set the, we have true solutions at these points. So say U equal to Ui, and the test functions equal to Uj, to obtain the following formula for all I and j. See, from the variational equality, we get these nice relations. And by reversing I and j and subtracting, this is just a simple, write this again with I and j reverse, subtract, we get the following formula for the off diagonals of the mass matrix. So the point being that you could compute the mass matrix directly from the data. You don't need the exact solutions or anything to compute the mass matrix. I didn't mention, but also by taking, so as you may guess, by taking spectral points closer and closer together, you can see that the diagonal of the mass matrix is given by the derivatives, which is one of the reasons we use the data in this form, because things are so simple. So if we were to take the variational equality multiplied by B sub j, again, reverse I and j and subtract, we get likewise a formula for the stiffness matrix, which is very similar, but just has these slightly different. Again, directly from the data. We do not need to know the internal coefficient or the internal solutions to get the stiffness matrix. And again, for the diagonal of the stiffness matrix, we take spectral points approaching each other, and we get the diagonal as given by the derivatives in this manner. So these formulas are well known in the model reductional community. They're not new, but it's nice to think of them in the context of inverse problems. And these have been in some previously published papers by co-authors. So this Galerkin model is of small size m because it could be for bigger, but the point is you could do this for some relatively small size m and then obtain the stiffness and mass matrices directly from the data. So this Galerkin discretization is a discretization of the PDE, which has the following property, and the property is that the solutions match the data exactly. What do we mean by that? For the Galerkin solutions U sub G, if we look at them at the point 0, this is where our receiver is, what we get is a rational function of lambda. And this rational function is exactly equal to the data at the given points B sub 1 through B sub m. It was constructed in this way. So it's the unique rational Hermite interpolant to the transfer function. And by Hermite interpolant, I mean it matches the data and the derivatives at these spectral points. To see why this is true, just for a sort of quick overview of the proof, it's not long. Well, why? Because we have m-dimensional tests in trial space. And so we can just do an eigen decomposition of the Galerkin solution, just use the Galerkin eigenfunctions. And you see that you must get that U sub G of 0 is given by, this is in this rational form for some positive residues and negative poles. And basically, since the exact solutions are in the trial space, as we all know from Galerkin methods, if the exact solution is in your subspace, you match it exactly, you get it exactly. So the data is matched exactly at those spectral points. And well, what about the derivative? Well, for that, we can use the fact that the exact solutions are also in the test space. So because they're also in the test space, we can look at the variational formulation, take lambda near BI and take limits, and we see that the derivatives are also matched. So the derivatives are matched as well as the values. So that's 2m data points that are matched for this rational interpolant. And so uniqueness follows from the uniqueness of the Hermite Bidet interpolant to f of lambda. So that's what happens with the transfer function when you use this reduced order model. So I mentioned that the data doesn't have to be in this format, so I just wanted to say a little bit about that. So Hermite is when you're given data in the form of point values and derivative values at the spectral points. And that in this, we're getting a Galerkin space of exact solutions. But you could also do, if you don't like derivatives in the data, what would happen? Well, you could also do multi-point bidet, meaning that you're matching, instead of matching derivatives, you're matching 2m point values. And this would give you a Galerkin-Petrov approximation. That is, it would mean you would have an equivalent transfer function to using trial and test spaces, each with m exact solutions. So you take the first m of them and put them in the trial, and the second m and put them in the test space, or in any order. And you get the same transfer function. Similarly, you could do simple bidet. So I'm hearing something. Does somebody have sound on? Okay, sorry, it seems to be done. Thanks. So, so if you do simple Pidé, that is, you're matching more like a Taylor approximation as opposed to sort of a Lagrange or Hermite interpolant. You do simple Pidé, meaning you're matching point values and derivatives at a certain spectral point. Then that would be equivalent to doing a Galerkin method with the first m derivatives of the exact solution. So derivatives in the spectral domain. So you'd be matching higher order derivatives in the spectral domain. So those derivatives in the spectral domains of the solutions would form your basis for the Galerkin space. You could also do pole matching, that is, given m poles and residues, that would be equivalent to having the Galerkin space of the first m eigenfunctions. So there's this nice relationship between what's happening with the transfer function in terms of an approximation versus the equivalence of a Galerkin or Galerkin-Petrov method. And you could do any combination of the above. So let's switch gears for a second and go back to talking about an original idea that was originated by Drexel and Nizherman back in, I think, 1998. Where they would say we're looking at the same problem, for example, with a 1D with a source and receiver at 0, the same problem. And let's just forget about Galerkin methods and just think about doing a rational approximation of the transfer function. So just consider the transfer function and doing a rational approximation. Well, what they did was said, well, they looked for a 3-point finite difference stencil for which the transfer function matched. Just like we were doing with the Galerkin, but now they were just doing it with a finite difference method. I'm sorry. And doing this yielded a special non-uniform grid, which yielded spectral convergence at the receiver, the point being that for inverse problems, it's your receivers for which you need the higher order convergence. So given data f of b sub I and f prime of b sub I for these same spectral points, one could generate the unique rational approximation to f of lambda, which match these, which interpolates this data. Then there is a unique 3-point staggered finite difference scheme, which with a tridiagonal matrix L sub m, modeling the differential operator, for which the approximated solution is at the point 0, so at the receiver, is exactly this rational interpolant. That is to say, the rational approximation, f sub m of lambda, uniquely determines positive, I'll call them gamma j and gamma j hat, such that solving this finite difference scheme here yields that the solution at the left endpoint is exactly equal to that rational function. So you're getting this high order rational interpolation at the left endpoint where your receiver is. And if we're, for example, to take q equals 0, you can see directly that these gamma j's and gamma j hats are simply primary and dual grid steps. For non-zero q, there's a more complicated thing going on. But this is just sort of to give an idea of how this relates to the the spectrally matched finite difference grids for a good reason. So the spectrally matched grid and the Galerkin solutions have exactly the same response at x equals 0. But what's the difference? So let's compare these two. They're both reduced order models for this problem, and let's compare them for a second. As forward models, the Galerkin solution converges high order everywhere on the domain, but the system is full because you've got, integrals of these exact solutions. The spectrally matched finite difference grid has high order convergence only at the receiver, and the system is tridiagonal. So it's a nice sparse system, but the convergence is only high order at this receiver. But this is a good sort of setup for inversion, as was studied by Porchea and Druskin for Sturm-Liouville problems. And what they did, I forget the exact date of this, but it was quite a while ago now, was compute the above or the similar reduced order finite difference model directly from the data. Use the spectrally matched grid for the reference media to extract the unknown coefficient. And the reason that worked was that they were able to prove that the grid depended only very weakly on the medium in the high frequency limit. So that allowed them to use the grid for a reference medium in order to extract the coefficients for the unknown perturbed medium. But there was a problem, a sort of a difficulty overall in terms of using these difference techniques in higher dimensions, and that is that there's something somewhat very fundamental about the finite, very fundamentally one-dimensional about the finite difference grid. So how do we generalize the grid to higher dimensions? Well, consider again solving the same problem with the Galerkin method with these exact solutions at these same spectral data points. And then this is the Galerkin system for the unknown coefficients, where this big F is your data. And you solve for C. So remember, F is precisely is the point values of the data. S and M can be obtained from the data directly. And then if you knew Q, you could then reconstruct the Galerkin solution by summing up C sub I times the exact solutions. Since S and M are full, unlike in the finite difference method. So here's a question: can we find a new basis in which the Galerkin system is sparse? And there's a reason for this other than just wanting to work with sparse systems. So imagine we take a delta function, since essentially the source is a delta function at 0. So imagine we take a delta function as, as a linear functional and sort of project it onto the subspace U in the sense that we find the element of U for which acts like a delta function. So there's a unique solution to that. So find the delta sub U, I'll call it, which when acting on, when integrating against any W in the space gives the W at 0. So we can identify this projected delta with some coefficients, I'll call them D's. The operator, quote unquote, here is essentially M inverse S, is essentially of our sort of reduced version of the differential operator. And consider the basis where we take powers of A, which is M inverse S, starting with delta and taking powers like pre-left subspaces. And now let's do Gram-Schmidt orthogonalization with respect to the M inner product on this basis. So if we do Gram-Schmidt with this basis, orthogonalizing with respect to the mass matrix gives us continuous L2 orthonormality. You can check that. So once we orthogonalize, we get a new orthogonalized basis for U. So this new basis, they are no longer solutions themselves, but linear combinations of solutions. And they're now orthogonal in L2. But they have another property which is important, because if we now redo the Galerkin system in the new basis, well, the mass matrix M, the new mass matrix, will be the identity, because these are now orthogonal with respect to in the L2 inner product. The stiffness matrix will be tridiagonal because this is a Lanczos process. So that's just a property of Lanczos orthogonalization. The right-hand side will be non-zero only in the first component because it's an approximate delta. And I claim that this system now, after orthogonalization, is almost precisely the finite difference system. The only difference being that this S hat is actually symmetric where the finite difference system was symmetrizable with respect to the diagonal, the gamma I hat inner product. So that gives us a little result that is, if one uses the orthogonalized basis and forms the Galerkin system in the orthogonalized basis, this is precisely the symmetrization of the finite difference system. That is, the Galerkin solution is just basically the coefficients up to the scaling with the gamma I hats are the finite difference solutions. So the interesting thing was, while those spectrally matched grids only gave high order convergence at the left endpoint, the reason was the values of the solution at the other grid points actually could be viewed as coefficients in a Galerkin approximation, sort of, except for these gamma I hats. So, but there's this relationship between the two approaches. So they're exactly the same. And this means that these new bases are not only being orthogonal, but it's also somewhat localized. So these new UI hats sort of correspond to localization near the grid steps. In other words, the solution components of the difference scheme that I wrote down before, let's take Q equals 0 for simplicity, can be interpreted as coefficients with a scaling of the Galerkin solution in this orthonormal basis. And here's just a picture of an example of a spectrally matched grid with the dual primary and dual points, stars and pluses. And these other functions here are the orthogonalized basis functions. This is a case where m equals 6. And so we see here the first, the projection of the delta, and then the resulting ones. They become less localized and more spread out as you move away from the source. And, but they are still sort of giving a localized basis function that somehow corresponds to the placement of the finite difference grids. So the entries of the reduced order model, which can be obtained from the data, are the entries of the stiffness matrix and the mass matrix after you orthogonalize. But the reason that this is one reason that this is really interesting for inverse problems, which I promised to get to, is that the orthogonalized basis functions here only depend weakly on the coefficient. So to see what I mean by that, this was noticed previously in papers by co-authors. So since the appropriately orthogonalized basis functions depend only very weakly on Q, we can use similarly orthogonalized basis functions for some known reference medium. So the point is, you may have noticed that from the data, while we can get the mass and stiffness matrix directly from the data, we cannot get the basis functions directly from the data if we don't know Q, because we don't have solutions. However, we could use the orthogonalized basis functions for a reference medium, a known reference medium. And you would think that that would be not so good, but it turns out that these really change very only weakly with respect to Q. And so these orthogonal basis functions for the reference medium play the role of the optimal grid steps for coefficient extraction. And unlike the finite difference grid, the localized basis functions have a natural extension to higher dimensions and other geometries. So anytime you have a variational formulation, you can look at sort of these localized basis functions. So let's look at, look at an example in one dimension of using this for inversion. So consider this as a perturbation of the reference problem with Q0 equals 0. And let's read data f of b sub I, f prime of b sub I for some spectral points for the perturbed problem. And from this data, we can directly generate the m by m stiffness and mass matrices, S and M, for the Galerkin system. These, you'll remember, correspond to the Galerkin system for the basis of exact solutions. Then we could perform Lanczos orthogonalization to generate S hat and M hat, that is, the orthogonalized basis versions of the stiffness matrix. Yeah, that's it. And these next couple slides show the weak dependence of these bases on Q. So here's an example: first, second, third, fourth, fifth, and sixth basis functions. This is a case when M equals 6 in 1D. So we have M spectral points. The blue is the basis functions for the perturbed medium, and the red for the reference medium. And you can see that they're on top of each other. So they're very, very close together. And you can also see this kind of localization that they have, which gets weaker which gets coarsens a bit as you move away from the source. And this is the fifth and sixth basis function. And it sort of models how well you can see what's going on. The further you get away from the source, the less precise information you can get. So from the data, we have a Galerkin system, low dimensional reduced order model. It's only 6 by 6 for the internal solution for any spectral value. Then for the reference medium, we have a highly accurate approximation to the orthogonalized basis. By solving the Galerkin system, we get the coefficients for the solution for the Galerkin approximation, Galerkin projection of the true solution. And this yields boundary data generated internal solutions, because we can then take the approximation to the orthogonalized basis and use it to build our approximation of the internal solution. So here's an example of the internal solution for an arbitrarily chosen spectral values. And this value wasn't one of the given data points, but it could be. So just lambda equals 3, for example. And here I have, here was a case where Q was 0.2, but we could do larger Q also. And in here we have the blue is the data generated internal solution. The red is the exact solution, and the yellow is the reference medium solution. Now, because this is like a diffusion type problem, we have that these, because this is a Schrodinger equation, we have that these things are all very close together. However, we could see as we zoom in a little bit that the data generated and the exact solution are much closer to each other than the reference medium solution. So that the reference medium solution is here in yellow. So as you zoom in, you can see that they're sort of, they're definitely much closer. So how to use the internal solution to do inversion? Well, just as sort of a proof of concept, and also because it's, we want to see, how good this is. Let's just compute u double prime minus lambda u divided by u. And this should be somehow close to Q if U was close to the actual, if our data generated internal solution is close to the exact solution. We could do this for any spectral value we wanted. And here's an example when, of a reconstruction of a Q. This was a piecewise cubic Q using this method. This is just 1D, of course. So it works despite the fact that it's just kind of seems stupid. But a harder example, again, this is with having just one source and receiver on the left. So you see that the bump is not reconstructed as well over here as it is there with the source on the left. We'll see now that you can actually put, you can have sources on both sides and still do this. But if you have a source just on the left, it's reconstructed better over here than, and gets worse as you get further away from the source. So for higher dimensional problems, so how do you use this in higher dimensions? Well, the nice thing is that everything really just kind of goes naturally into higher dimensions, with the complication that, so let's see, for higher dimensional problems, well, what do you want to do in higher dimensions is use k different sources and receivers. You could do one source receiver in higher dimensions, but we can also do a number k of source receivers. So by source, what I mean here is some Neumann data on the boundary of omega. I'll call that G sub r. So what we're assuming we have data here for is a number of spectral values, which I put in B sub I here, again, similar to in 1D, and a number of sources, K sources / receivers. So now the spectral data is, instead of the spectral data just being a scalar valued transfer function, it's now a K by K block transfer function where the block nature corresponds to source receiver. So so this FIRL, the R corresponds to the spectral value, the I corresponds to the spectral value, B sub I, and the R and L correspond to source and receiver. The R would be the Rth source, and the L here is the Lth receiver. And the receiver means just integrating against the Lth Neumann data. So you have these block data, and also you have their derivatives. So let's assume we have these block spectral values and their spectral derivatives. Well, again, one has a Galerkin system for the basis of exact solutions. And we can get it from the data directly again. As you might have noticed that those manipulations that work in 1D also work in general for this problem anyway. And then so you get that the mass matrix is computed by differences of these blocks and the diagonal by its derivatives, and similarly for the stiffness matrix. So now for orthogonalization, because we have blocks, we orthogonalize with block Lanczos, with K by K blocks. So once we orthogonalize with block Lanczos, the result, instead of being tridiagonal, will now be block tridiagonal. And there's no more finite difference representation, but the localized basis functions give us a geometric interpretation of the system. So because of the localized basis function, we can take this reduced order model, which is a tridiagonal, a block tridiagonal system, and in order to interpret, you know, sort of, in order to extract the unknown medium from this reduced order model, the localized basis function should help. And so after orthonormalization, the basis functions are very close to those from the reference medium, and this again happens in higher dimensions. So again, the reference basis functions combined with the reduced order model will yield internal data for any chosen lambda. Not exact, of course, but a good approximation. So we could again try the sort of stupid thing of taking Laplace u minus lambda u divided by u. So let's do this. We'll do it first for a 1D varying medium. Yeah, so this is really one-dimensional. We use two sources that are constant on each side, one on each side. So the problem, although, yeah, so the problem is basically one-dimensional with two-sided sources. So in this case, we'd have 2 by 2 blocks. Everything would be in 2 by 2 blocks. And here's the result you get by taking the Laplacian of an internal solution, and it's surprisingly not so bad. You could also take 4 sources on one side here, and these are piecewise constant sources in this case, to sort of reconstruct. This is a Gaussian perturbation. And here, this is 4 forces, and this is the reconstruction from the Laplacian. And again, this is just this direct Laplacian method. One could also go ahead and do some kind of iteration or optimization after this. So that was, so in this case, because of the 4 sources on one side, there would be blocks of size 4 by 4. Here's a profile of 2 Gaussian bumps in a 2D medium and 8 sources around. Well, we have 2 sources on each side, piecewise constant. And what I want to show here isn't so much, well, I'll also show the reconstruction, but it isn't so much the reconstruction, but the internal solution generated from the data. So up here, I have the data generated internal solution. I don't know how good the color is for everybody, but the data generated internal solution here, oh, sorry. And over here is the true internal solution, computed, you know, assuming we knew Q. And this is the one generated from the data without knowing Q. And this is the background true solution for comparison. And just by computing the relative error, relative L2 error between the data generated and the true solution, this is like 0.004, almost, just under that. And between the true and the reference median for comparison is 0.085 essentially. So it's like 20 times, over 20 times better than the reference median as an approximation. And you can also see here, I don't know if you can see depending on the quality of the picture, but there's this anisotropy, there's not anisotropy, but this it's not anisotropy, but the sort of direction that's happening because of the perturbations where the background solution doesn't demonstrate that, doesn't have that at all because of the symmetry. And here's the reconstruction from the Laplacian for this case. So you're seeing something, you can see the two bumps. So I also want to talk about now other ways. So because these internal solutions are nice to have, but this taking the Laplacian, it's not necessarily, I don't know if that's the best way to compute Q, given that one has the reduced order model. So there are other ways to use the reduced order model, the same one, for example, that I talked about here, to reconstruct the unknown parameters. So recently, for hyperbolic problems in the time domain, there have been these works with some very impressive reconstructions using two other methods. One is back projection, and another is just sort of looking at how the model is perturbed itself. So there are other ways to use the model to reconstruct things. But if we are thinking about the internal solutions a little bit, we also want to propose what seems to me to be a natural way to use internal solutions, and that is in the Lippmann-Schwinger equation. And when you view things in the context of a Lippmann-Schwinger equation, it sort of gives a nice formulation, I think, that shows that this idea could be extended. So consider the Lippmann-Schwinger equation. So just take a solution U and its corresponding background solution for a Schrodinger problem. And let's assume G is the background Green's function. Then standard Lippmann-Schwinger, assuming G has the correct boundary conditions, is that U minus U0 is this integral G minus multiplying the perturbation, the coefficient in U. Since for our problem here, our data is in the form of integrals of the solution against the these receivers or the Neumann data. If we integrate both sides by parts, if we integrate both sides against G and integrate by parts, we get a formula for F0 minus F, F0 being the data for the background and F being the data for the perturbed problem, is equal to integrals of the U times the background solutions Q minus Q0. Well, if one were to use the inverse Born method or variations upon that, what would you do? You would replace U by U0, right? So you would in here, whichever place, replace U by the background solution. And that linearizes the problem. But with the data-generated reduced order model, we can replace U with its data-generated internal solution, which should be better than the background solution. And then another thing we could do is just quite natural to look for the unknown perturbation in that case in the space of background solutions. We have those and we have an orthogonalized version of those. So we could do that. So in here, you could use this as data and look for this unknown in a basis of orthogonalized U zeros and put in the internal solution for U and invert. This method is very related to the time domain approaches used by the authors in these other two papers. This just gives a simple and explicit formulation, and there's some versatility to it in the sense that, well, it's just easy to see how it can be augmented. For example, if you have a large number of sources and receivers, or more data than you use to generate the reduced order model. I mean, suppose the reduced order model were generated by a small data set, because it's not super big. You could add lots of other sources, and the data is the F, and you could, if you had more data, you could, and you have S and M are the same, you could compute internal solutions for other data. And you could also here use the, so here I have F here. You could also take lambda derivatives of F and use that data directly too. So just as a proof of concept, this is just a 1D example. And for this, we didn't use the derivative data, but rather only the Fs. This is a 1D two-sided problem. So it's a case with 2x2 blocks. This is the true unknown medium, which is a Gaussian in one direction. It goes up to 1. And we put a constant source on the left side, and a constant source on the right side with 4 spectral values, so only 4 values for lambda. And then the 2x2 blocks, so this is sort of an 8x8 system, reduced order model. There are 16 data points because we have the F's and the derivatives for these spectral values and sources. And if we were to use the Laplacian to get the Laplacian, if we were to, okay, so if we were to, let's start with the Born, if we were to do inverse Born, that is take this data F and directly put in the background solution for U in Lippmann-Schwinger, we see that we get something with some, false reflections is coming from the multiple scattering. But if we use the internal solution and reconstruct Q from taking the Laplacian, we get this sort of smoothed out thing, which goes up to 0.6 and is spread out. But if we do the reconstruction from the Lippmann-Schwinger equation, putting the Lanczos internal solution into the Lippmann-Schwinger equation, we get something much closer to the true solution. And this goes up to 0.96. And you see that it's getting closer to being thin like the actual Q. So this is just a proof of concept because it's a simple example. So this was just recently computed. 2 sources and 4 spectral values. So, okay, so I think I'm finishing right on time with conclusions. We can use spectral data to directly generate Galerkin reduced order model, as was done before in the time domain. In 1D, after orthogonalization, this is equivalent to a spectrally matched finite difference grid. Lanczos orthogonalization yields a new basis, which is close to that from the reference medium. And this is the place where there's needs to be some math done to sort of understand exactly how close, and we are thinking to prove something about that right now. We can use the reference medium basis and data generated reduced order model to obtain approximations of the internal solutions from the data, which could be of interest in their own right, also not necessarily for reconstructing Q. You can get reconstructions directly. One method that's you can do quickly is this. Is just take Laplacian minus lambda u. Or you could do put the Lanczos internal solutions into the Lippmann-Schwinger equation, which yields an explicit and extendable approach that should be computationally efficient, I think, for certain examples. So, and that's it. I'm finished.
Thank you very much. Thank you very much, Shari. Are there any questions or comments? Okay, are there any questions or comments? Okay, if not, thank you very much, Shari, for the great talk. Thank you very much. Thank you. And thank you very much, everyone, for coming. Thank you.
Thank you so much for inviting me. Oh, thanks for clapping.